Good day to you, students. This presentation is on the two different base number systems, decimal and binary. Now let's jump right in. Now it seems pretty obvious why we as humans use what is known as the decimal or base 10 numbering system for our everyday lives. We are, after all, born with 10 fingers, which serve as an immediate reference point for us. We use the base 10 system for numbers higher than 10, of course. The unit 10 is just a foundation for this numbering system. And if we had 6 fingers on each hand, we may just be using the base 12 system. It's really pretty arbitrary, is why we're using 10. Computers, on the other hand, are pretty limited to the systems they are capable of using. Even though they can be very fast and powerful, they have to use very simple language. Let's look at some examples of what I mean. Computers truly understand the basics of on or off, yes or no, open, closed, and in numerical terms, ones and zeros, and this is known as the binary system. So now the goal for this presentation is to answer the question, what is binary? And how can computers convert and calculate base 10 numbers using binary? I mean, how is it even possible that a long string of ones and zeros can possibly be enough information to convert anything? First, let's look at a light bulb, for example. In this example, a 0 will represent the light bulb that is off, and a 1 will represent a light bulb that is turned on. Now, you can see here 4 different sets of light bulbs that are in different combinations of on and off. On the top left of the screen, you'll see 2 light bulbs that are off and 2 zeros underneath. Think of that set of zeros as a code or symbols that represent no light. The same goes for the rest of the sets, just codes that represent the different instances of the 2 light bulbs. Let's look at some vocabulary now so we can better communicate the ideas of the binary system. Every single number in the system is called a bit and can be a 1 or a 0. Any group of 4 bits is called a nibble. And continuing on with the theme of eating, a byte is a group of 8 bits. Now let's use the nibble for some further examples. Every binary series starts with what is known as the least significant bit, which is the lowest bit in the series and is usually, but not always, located at the far right. The most significant bit is the highest number in the series, opposite of the least significant bit. It doesn't matter how long the series is, there's always a least and most significant bit. Now let's dig into the meat and bones of how the binary system can convert a decimal or base 10 number. Each bit in the binary series has a relationship to a base 10 or decimal number. The least significant bit has a relationship to the decimal number 1. The next highest bit has a relationship to the decimal number 2. And the third bit has a relationship to the decimal number 4. Can you see a pattern starting to form yet? The fourth bit in this nibble, the most significant bit, has a relationship with the decimal number 8. If you still haven't guessed the pattern, every bit higher we go will double the decimal value it's in a relationship with. Remember, these numbers represent the decimal or base 10 number that are used to convert from binary form. Let's clarify this with some further examples. Let's say we have the binary number 0101. It turns out to be a simple addition problem once we make our conversions. Now remember back to our light bulb examples, where 1 was on and 0 was off. The least significant bit is a 1, so it's on, and we're going to put it in our addition problem below. The second bit is off and is a 0, so we won't add this. The third bit is a 1, so we will add its decimal relative, the 4, to our problem below. The fourth bit in the nibble, and the most significant bit, is related to the 8, but we don't add it because there's a 0 and not a 1. The light bulb is out. So all we have to do now is add up the problem. 1 plus 4 equals 5, of course. Now let's try another example using a 4-bit nibble. Take your time before proceeding and only add the decimal numbers that relate to the bits that have a 1 in them. The ones with the light bulbs that are on. And that's 8, 4, and 2. Did you get it right? You'll be able to practice this a lot with the binary sequence practice simulation found in the additional resource section of this class. But first, let's try this using a binary byte. Remember, there are 8 bits in a byte, and the relative decimal values have continued to double for each additional bit. The least significant bit is still related to the decimal number 1. It always is. The most significant bit, however, has changed and is now the 8th bit in the series. The 8th bit is related to the decimal number 128. The least significant bit is a 0. No light and nothing to add. The second bit is a 0, again, nothing to add. The third bit is a 1, and the light bulb is on. The third bit relates to the decimal number 4. The fourth bit is a 0, nothing to add. The fifth bit is a 1. 16 is the decimal number related to the fifth bit. The sixth bit is a 1. 32 is the decimal number related to the 6th bit. The 7th bit is a 0, nothing to add. The 8th bit is a 1. Again, 128 is the decimal relative to the 8th bit. The number is double 64, which is the decimal relative to the 7th bit. Remember, each decimal value doubles from the previous. Before you proceed, can you take a guess as to what these all add up to? In other words, the number 180 in decimal form is equivalent to 101101000 in binary. I strongly encourage you to now take the time to do some practice by opening up the binary sequence practice simulation found in the additional resources section of this class. And if you still need help, always ask your instructor. Thank you.